All right, so we're going to pick it up where we left off in chapter 3. And what we're looking for is what are called relative extrema, meaning relative maximum points and relative minimum points. And so we have 3 examples here to start with. And so we start with the one on the far left, and you can see it's a curve. Looks approximately like this. What are we looking for here? Well, we're trying to find the point on this curve, if there is one, where the tangent line at that point is flat or horizontal. Why is that? Because at that point, the first derivative of the function is equal to 0. Okay, so if this is point C, then f prime of C equals 0. In other words, the slope is 0 because the tangent line is flat. That point has to either be a relative maximum or a relative minimum. Now, we can tell just by looking at the graph that it would be a relative maximum, but later on we'll see a more formal way of finding whether this point is a relative maximum or minimum. Okay, so what they did was they went ahead and they took the derivative of this function, and it was quite a mess, but they did all the work for us. So they went ahead and when they found this derivative of the quotient rule, they showed that it turned out to be 9 times 9 minus x squared over x to the 4th. And as you can see, if I were to set that equal to 0, let's do that right now, we would discover that this would give us, it would actually give us 2 solutions, one of which is x equals 3. Okay, so in other words, if I set this equal to 0, you'll go through a little algebra and you'll discover that x equals, it actually equals plus and minus 3. Now, I thought that was very interesting, so I went ahead and graphed it in Symbolab. And if you look at it carefully, you'll see that this function actually has 2 distinct regions, and they're mirror images of each other, it looks like, from across, let's say, the main diagonal there. And so you can see that when x equals 3, we're here, and this is where the tangent line would be horizontal. The same thing would be true down here. But for this example, they're focused on just this part of the curve. And within this region, this would be the largest value of the function, which happens to be 2, by the way. And so that is our relative maximum. All right. And also, by the way, they went ahead and solved for the value of the function at x equals 3 by plugging it back into the original function. So in other words, if the original function is 9x squared minus 3 over x cubed, then that means that f of 3 would be let's see, what do we get? That would be 2. Okay. And that's exactly what they're showing us. In other words, this is the point 3 comma 2. That is considered to be our relative maximum. Now, the second case is actually quite interesting. We're looking at the absolute value of x. No, I missed it a little bit. Hold on, let me fix that. Okay, now you might recall that when we have a function like this is sometimes called a piecewise function because it looks like two separate functions were sort of glued together to make this function. So it's defined in terms of regions of the x-axis. And so in this case, the formal definition of absolute value of x looks like this. So there's the behavior is very different depending on whether x is positive or zero or negative. Now, if you remember from last chapter, when we first introduced the concept of the limit, and we showed that how the derivative is in fact a limit, there's one problem here. What is that problem? Let me just jump ahead and show you what the problem is. Here it is. If you try to take the derivative with this formal definition, you'll notice that it reduces to absolute value of x over x. Okay. So in other words, this is one of the, by the way, this is one of the two equivalent versions that we can use to find a derivative with the limit. And so in this case, c is 0. So the limit as x goes to c from 0 rather from the left, it's -1 because the slope on this side is -1. Okay. And then if we do the same thing coming from the right, it equals +1 because again, if you're coming from this direction, the slope of this is +1. So the two are different from each other, and therefore the derivative at that point does not exist. So that happens whenever there's a sharp break in a function like that. The limit or the derivative rather does not exist because the limits coming from both sides are different. So therefore, you might think, well, then what does that tell us about whether this is a minimum or a maximum? Well, it turns out that as long as this point represents the smallest value the function can take on, it still counts as a relative minimum. So you can see this is a very interesting case. The point 0, 0 is a relative minimum even though f prime of 0 does not exist. So that means there's two different ways in which we can have a relative maximum or relative minimum. A point can be a relative maximum or minimum. Sorry about that. If one of two things is true, f prime of c, the point, let's call the point x equals c, can be a relative minimum or maximum if f prime of c equals 0, or f prime of c is undefined. Either way, it will be a maximum or can be a maximum or a minimum. Let me make this a little bigger. That's better. So you can really see that. So those are the two cases we'll want to keep our eyes on when we're trying to identify all these maximum and minimum points in a function. Now, they're also giving us a third example where there's more than one maximum and more than one minimum because it's a sine wave. And that means that it keeps just alternating between up and down and up and down. And you can see we have two of the points that we need identified here, the relative maximum at pi over 2 and the relative minimum at 3 pi over 2. So why are these relative maxima and minima? Because if you take the derivative of the sine of x, remember from my handy chart here, that remember is on bright space, that would be cosine x. So for any x where the cosine is 0, the point is a relative maximum or a relative minimum. And you can see there's actually going to be an infinite number of them because the domain for the function y equals sine of x is infinite. It goes all the way up from negative to positive infinity. So this is a case where there's going to be multiple points that represent a relative maximum or a minimum. So basically, what they're going to do now to summarize this is show us these two graphs, and they're showing us the new definition of something called either a critical number or a critical value. And so what they're basically showing us is that C is a critical number of the function f of x if one of two things is true. A, f prime of C does not exist, or B, f prime of C equals 0. Okay, so now you can see here we have a sharp break, which means the function, the derivative does not exist at that point. And so that C is called a critical number. It's a candidate, think of it as for possibly being a relative maximum or minimum. And then over here on the right, you can see that at C, the tangent line is horizontal or flat, which means that the slope is 0, which means they both qualify as critical numbers. So our job when we're looking for these points is to first start by identifying all the critical numbers. Then we check them all to see if they might be a relative maximum or minimum. Okay, let's see. Now, if we're looking at a closed interval, there's more steps involved. Besides finding the critical numbers, we also have to evaluate the function at each of the endpoints because those could potentially be relative maximum or minimum points too. So what you want to do is find all the critical numbers in your interval, then look at the two endpoints, and then whatever number is the smallest of those is your minimum, the largest is your maximum. All right, so let's look at this case. Now, this is a nice polynomial. It's continuous, so we're not going to find any points where f prime of C is undefined. In fact, they've already taken that for us. Let's go to Symbolab and draw a picture of this function, because it's kind of hard to visualize. Once you start getting up to x to the fourth territory, it gets very difficult to visualize it. Okay, where is it again? Oh, 3x to the fourth minus 4x cubed, that's right. Oh, now that's kind of strange. But there it is. That's what it looks like. So we're only interested, though, if you notice, in the closed interval -1 to +2. So we're going to start. Now, of course, our job is to find all the potential points that could be a relative maximum or minimum. So the first job is to find where the derivative is equal to 0. Okay, so let's do that first. So remember, they gave us this procedure. The first step is to find, well, the critical numbers, meaning that the points where the function has a tangent with a slope at 0, or else the derivative is undefined. But we know that there won't be any of those, so we'll just focus our attention on the points where the derivative is equal to 0. So first we have to differentiate this function and set it equal to 0. Oh, here it is. Okay. So based on the rules that we've been learning, we can easily calculate the first derivative. And then we'll set that equal to 0. First thing we'll do is divide both sides by 12. And then we're going to factor out the x. Actually, we'll factor out an x squared. Let's do that. That probably would be quicker. So that implies that okay, so we have x equals 0 and x equals 1. So f of 0 equals 0. So the point 0, 0 is either a maximum or a minimum. And then what about 1? To the point 1, -1 is a maximum or a minimum. And you could tell if we go back and look at the graph. Here's 0, 0, and you can see it is flat there. The tangent line would be flat there. And then right here at 1, -1, it's also flat. So these two are the points that we're looking for. These are the two critical points, as they're called. And now we know how, yeah, we've already evaluated these, but now don't forget, this is a closed interval. We also have to evaluate the function at the two endpoints, -1 and +2. All right, so because it's a closed interval, we need to also check f of -1. Oh, I forgot to write down the interval. And +2. Hold on. Yeah, -1, +2. All right, good. Let's just do that real quickly right now. So the function is here. So f of -1 is 3 negative 1 to the fourth minus 4, negative 1 cubed. And we also need to check f of positive 2. All right. So now what they've done, they've done a nice thing for us. They put together a little chart that summarizes all the results. So we have the two critical numbers, which we discovered by setting the function's derivative equal to 0. And we found their values. We've evaluated them. And so you can see that of the 4 potential minimum and maximum points, the minimum must be this one, because negative 1 is the smallest, and the maximum must be this one, because that's the largest. Oh, here we are. They did go ahead and draw it for us. And so you can see it a little bit more clearly. The 0, 0 is neither a maximum nor a minimum. Even though it's a critical point, it's not either a minimum or a maximum. Instead, the minimum occurs at 1, negative 1, and the maximum occurs at 2, comma 16. So in other words, what they're telling us is that not every critical point is a maximum or minimum, but well, at least with an open interval, it does go the other way around. So anyway, so let's see, what do we have here? Find the critical numbers of this function. Now, again, this is a polynomial. There won't be any points where the first derivative is undefined. So all we really have to do is solve for g prime of x equals 0. All right, that looks pretty straightforward. And that's all they want us to do. All right. So g prime of x, based on the rules that we know and love from the previous chapter. Okay. And they're asking us to find the critical numbers. Okay, so we'll set this equal to 0. So I think, actually, I'll tell you what, it might be easier to do some factoring first. Let's do this. So we can divide out the 4, factor out an x, and then that tells me that x equals 0 and x squared minus 2 equals 0, x squared equals 2, which implies that x equals plus and minus radical 2. So we have 3 critical numbers: negative radical 2, positive radical 2, and 0. And that would be B. Now, what about this one? So we're looking for the absolute extrema. Now, remember, extrema can refer to either a maximum or minimum. So let's try this. So we start with the first derivative, set it equal to 0, find all the points where the first derivative equals 0. Those are the critical numbers. We'll divide out the 3. All right. So then we also have the two endpoints, 0 and 4. So what we have to do now is solve for g of x at the points -2, 0, +2, and +4. And then the last one is 4. Okay, well, that's interesting. In fact, I'll tell you what, let's take a look at this graph. Oh, that's right. Okay, so x cubed minus 12x looks like this. Ah, well, there you go. That kind of explains why we have such interesting results. So anyway, but the bottom line here is that so we do have two maxima and one minimum at the points you can see. Now remember, the interval is only over 0 to 4. It's hard to tell from this graph where those are, but so that means we have these points. Uh, oh, I just realized. You know what? I just realized that the interval over which this is being defined is 0 to 4. So that means we didn't need the x equals -2. So we're going to drop that one from consideration. Because yeah, I forgot to about that. So we'll get rid of this one. Because it's not in the interval that we're looking at. Now that does make a lot more sense the way it's written here. So at 2, it reaches a minimum. At 4, it reaches a maximum. Right, 2 is right about here. This would be 4, or no, 4 is over here. It's like I said, it's hard to tell from this graph, but so this is what our results are. Oops. So the point 2, -16 is the minimum, and 4, 16 is the maximum, relative maximum. Okay, so you see, they shouldn't do this. They mixed in the absolute. They didn't really discuss. Yeah, that was kind of sloppy on their part, I must say. All right, let me just mention quickly. Up to this point, everything has been in terms of relative maximum and relative minimum. And then they suddenly try to sneak in their absolute. No, that's not all right. Let me just show you what that's all about. There can be two types of minimum and two types of maximum. Is the largest value within an interval. It is known as the relative, or sometimes it's called local maximum. A minimum is the smallest value, or actually, I shouldn't write it like this. Let's try it like this: a relative or local maximum is the largest value within a given interval. That's better. And then a relative or local maximum, you can probably guess, is whoops, sorry, this is minimum, is the smallest value. But we also have the concept of an absolute or global maximum is the largest value within the domain of the function. And an absolute or global minimum is the smallest value within the domain of the function. In other words, it's either the largest or smallest value that the function can obtain anywhere. The local or minimum, the local ones, the relative or local ones are within an interval. Maximums that are in absolute or global, or minimums that are local or global, absolute or global, are for the entire function. So they kind of goofed there at the end with that last example, but we'll see more about that in the next section. So these should be local or relative because we're doing this over this interval. But anyway, now next, we're going to look at some theoretical results. Raleigh's theorem and the mean value theorem. So basically, these theorems are there to help us understand the behavior of what we're doing. And so Raleigh's theorem tells us under what circumstances we can guarantee either a minimum or maximum exists within a closed interior, a closed interval, sorry, the interior of a closed interval. All right, so what they're telling us, and suppose the function is continuous over the closed interval, and it's also differentiable everywhere except possibly at the two upper and lower limits. Now, this, by the way, this only works under the following conditions. In other words, within this interval that we're defining, it's got to be the case that the function has the same value at both endpoints. If that's the case, though, we're guaranteed that there's somewhere inside this interval, at least once, where we have a tangent curve which is horizontal. But only if we know for a fact that the function must be continuous in the interval, differentiable everywhere except possibly at the endpoints, and f of a must equal f of b. If they don't, well, then this all goes right out the window. Oh, here's a good example. So here would be a case where all of those conditions are met. So now, if the function is not continuous everywhere from a to b, you might run into this situation. So you can still have a critical value, but that doesn't necessarily guarantee us a horizontal tangent. So like here, for example, here's the function x squared minus 3x plus 2. And they basically want us to show that Raleigh's theorem holds. Okay, so x squared minus 3x plus 2. And so and we're interested in the interval. Oh, between the two intercepts. Okay, so they're leaving us to figure that out. All right. So the two intercepts are now it looks like they mean the horizontal intercepts. They didn't say that, but all right, anyway. So to find the intercepts, set this equal to 0. Okay, so we know that this is a parabola that faces up. Something like that. Actually, we may as well go ahead and draw it in Symbolab. Oh, I just realized it's minus 3x. Okay. All right, let me fix that. Okay, so it's x squared minus 3x, so that derivative was wrong. F of x equals x squared minus 3x plus 2. All right, let's take a look at the graph. All right, so they're looking for these 2 points. All right, so let's find them. X squared minus 3x plus 2 equals 0. So we could use either the quadratic formula or we could simply factor this. Okay, and so that means that x equals 2 and x equals 1. Okay. So you can see that here, right there, those 2 points. And then now, if you notice, at those 2 points, the function equals 0. But the important thing is that it's equal, it's the same at both points. And because it's a polynomial, it is smooth and continuous everywhere. It is differentiable everywhere within that interval, which means that Raleigh's theorem holds. And therefore, there's got to be a point in there somewhere where we can find a tangent to the curve that is horizontal. Now, where would that be? Aha. So in other words, within the interval 1 to 2, we must be able to find a point. Let's see what it is. And of course, 3/2 is in the interval 1, comma 2. And so at that point, we have and you can see from here, the tangent right there would be horizontal. That's the point 3/2. And so we're all set. All right, so let's look at their graph. Yeah, there it is, right there. Okay. Now the mean value theorem. Looks like this. F is continuous over the closed interval, AB, and differentiable in the open interval. And so it's not trying to tell us where the tangent line is horizontal, but what they're saying is that there must be a point where this relationship holds. So it's a little bit more general than Raleigh's theorem. And so there's a picture, a graph here. So let's start with this example. F of x equals what is it? 5 minus 4 over x. And so what we're going to do, oh, and we need to know the endpoints, 1 comma 4. Oh, and a quick reminder that that term actually is equal to this the secant, the slope of the secant line between the points A and B. So f of 1 equals 5 minus 4 over 1. And f of 4 is 5 minus 4 over 4, 4. So we're guaranteed the existence of a point C. So we can think of this as A, and this is B. Okay. So we're going to have 4 minus 1 over, 4 minus 1. Okay. So in other words, we must, in that interval that we've just defined, there has to be a point where the slope of the tangent is 1. okay? So we're going to find that point by taking the derivative of this function and setting it equal to 1. All right, let's do that. So we'll rewrite this as 5 minus 4x to the minus 1. And then we set that equal to 1. Okay, so, oh, by the way, the interval of interest here was from 1 to 4. So we don't need to worry about the -2. So that, in other words, at x equals 2, f prime of x equals 1. So I think we should look at a graph of this thing. It's kind of hard to visualize. 5 minus 4 over x. Okay. So the interval of interest is from 1 to 4. Okay, so we can take a picture of that. So over our interval, right about when x equals 2, the slope of the tangent line equals 1. So yeah, so a useful alternative version is that if f is continuous over a given interval and is differentiable as well, then there must be a number c such as this relationship is holds. Let's see. So yeah, it'll show, it's a very theoretical result, but it'll prove to be very handy. We'll need it from time to time. So they want to close this out here by asking us if Raleigh's theorem can be applied. And so here's the function. All right, hold on. So the function is x squared minus 2x minus 3. And the interval is negative 1, 3. And they're saying that if we do find that this works, we want to find all the C's in the interval such that f prime of C equals 0. Okay, so we need to show, well, first of all, it's a polynomial. We know that it's continuous and differentiable. So what we really are interested in here is showing that these two are equal to each other. If they're not, well, then that's it. The theorem doesn't hold. Okay, so we have a result. And now what we want to do is find the points where we have a tangent line which is horizontal. And that would be x equals 1. Okay. And so the answer is A. All right. Now the mean value theorem f of x equals x cubed, and the interval is 0, 16. And they're aiming for find the values of C such that f prime of C okay. So in other words, we know that this is x cubed. And let's say this is 16. So in other words, what they're saying is that there's some value C. This is the slope of the secant line between 0 and 16. There's got to be some point in here where the tangent line has the same slope. Okay. Now, again, it's a polynomial. It's smooth and continuous everywhere. We don't, and differentiable. We don't have to worry about that. And that's all we need. So why don't we do this? First, we need to know f of 0 is 0. F of 16 is 16 cubed, whatever that is. Ah, here we go. 4096. So this ratio is equal to 256. All right. So we're going to look for, first we need to know f prime of x, 3x squared. Okay, so we're going to find the x at where this is true. So well, that's kind of an odd result. But now keep in mind, we don't need the negative one because we're only interested in the interval from 0 to 16. So the C, as they're calling it, Wow. Okay. Oh, so they it looks like they've simplified it a little bit. All right. Let's see. How do we simplify this? So this could be rewritten as, oh, sorry, wait a minute. That's not right. Hold on. That's better. Okay, so what do we have now? Um, 2 times 8 over radical 3. So we end up ultimately with 16 radical 3 over 3. So it's C. Okay. So anyway, well, that was a very theoretical section. That was 3.2. So what's coming up next? Let's find out. Oh, we're not going to do it tonight, of course, but I just want you to see what's coming up next. So now remember before I mentioned that they're giving us like basic information about how to find a relative maximum and a minimum, but they never really quite got around to telling us, aside from looking at the graph, how to make sure we know which ones are minima and which ones are maxima. So that's what this is going to be all about here. They're starting to give us more formal ways of identifying these extreme points and how to tell them apart from each other. We also are going to find out how to determine over which intervals a function is increasing and decreasing. So this is actually going to be very, very important and not very theoretical, not like this last section. That was a lot of theory. Here we're going to learn some practical skills for trying to identify the relative maximum and relative minimum points in a function. So we'll, of course, save that for next time. So I'll see you then.